In this video, I want to create a Kirchhoff's loop law equation for an RC circuit. Now we know from the past that Kirchhoff's loop law says that the sum of the potential differences in any closed loop must sum to 0. But let's try to use this idea on an RC circuit. In this RC circuit, we have a battery with an EMF of 10 volts. And the battery's job is to maintain a constant potential difference for as long as the battery has energy to do so. We also have a resistor here. And the potential difference across it will be given by the current times its resistance. In our capacitor, we've seen in the past that the potential difference across it will be given by Q over the capacitance C. So let's start here and create a complete loop. We'll add up all the potential changes as we go through the circuit, taking into account the signs as well. First, we go through the battery. So we'll add the EMF of the battery. Next, we'll go through the resistor in our loop. So we want to subtract. And when we subtract the voltage of the resistor, I'll just put VR to represent the magnitude of that voltage. Next, we'll go through the capacitor, and its voltage will be VC. Finally, these things have to sum to 0. Now, if we wish, we can take the formulas that we have for VR and VC and plug them in. This gives us a nice equation for a RC circuit. The quantity which remains constant throughout time, though, is the voltage across the battery. So if we are to rearrange, we can see that the voltage of the resistor plus the voltage of the capacitor always has to equal the EMF of the battery. Now, what happens in an RC circuit as it's being charged up? Well, let's assume first of all that it starts discharged. If we're completely discharged, then what we'll see is that the voltage across the capacitor is 0 at that time. But in this particular special case, when the switch is open, then the voltage across the resistor is also 0. So in this particular case, the rule won't hold because the switch isn't closed and the RC circuit hasn't been completed. Now let's close the switch. At time 0, immediately after the switch has been closed, the capacitor is still discharged. So we'll have Vc equal to 0. But now we need for VR plus Vc to equal the EMF. So therefore, VR, the voltage across the resistor, must equal the EMF of the battery at this time. Now let's look at what happens over the long term after the switch has been closed for a long time. As t approaches infinity, a long time after closing the switch, the capacitor will be charged now. But also the current approaches 0. We still need the VR plus the Vc to equal the EMF. But this time, the VR equals 0 and Vc equals epsilon. This shows the trade-off between voltage across the resistor and voltage across the capacitor, and how when we lose voltage in one, we have to gain voltage in the other. If we were to label the potential at different points around the circuit and assume that the negative terminal of the battery is 0, then what would be the potential at these important points? Well, the battery always supplies a constant EMF as long as it has energy to do so. So the potential at that point will be E. However, when we're first getting started with charging the capacitor, we'll have 0 volts in the wire between the elements at this time, and all the voltage drop will be across the resistor. Down here, once the capacitor has been completely charged, we'll now have the same potential on the left upper corner as we have on the right upper corner. Next, let's look at what happens when we discharge a capacitor. In order to discharge a capacitor, we first have to disconnect it from the battery. Then what we can do is connect a wire from one point in the circuit to another. And if we allow the discharge to happen through a resistor, then this is still an RC circuit. But we are now discharging it. How does the voltage across the capacitor and the voltage across the resistor change with time? Now we have to think about Kirchhoff's loop law once again. Only this time our loop has changed. As we go through the capacitor from negative plate to positive plate, we will gain the maximum voltage. We'll gain the voltage that it holds. But now we're going to be going across the resistor, and we have to lose all the voltage that we had gained somewhere in this loop. So where do we lose the voltage? Well, the answer is the voltage in the resistor will now equal the voltage in the capacitor. And we have a new loop law equation where the voltage in the capacitor minus the voltage in the resistor has to equal 0 because there's no battery anymore. So we'll start up high with the voltage on the capacitor because it's at its maximum value. It's at its maximum value at t equals 0. And what will happen is it will decay exponentially, like that. The voltage across the resistor will have to also start up high and then go down to 0 as well. What happens to quantities such as the current in the circuit with time and the charge on the capacitor with time? Well, the current in the resistor will be given by I equals delta V over R. The resistance of the resistor won't change, but the voltage in that resistor will change according to the graph above. So it will actually start up high and then decay to 0 as well. What will happen to the charge on the capacitor plates as time goes on? Well, we have the formula Q equals the capacitance times the voltage across the capacitor. Capacitance is a property of the capacitor, so that's not going to change. But we will start with a large voltage on that capacitor, so we'll have a large amount of charge on it. As time goes on, this will decay towards 0 as well. Eventually, the capacitor will be completely discharged, and at that time, The voltage across the capacitor is 0. The voltage across the resistor is 0. The current in the circuit is 0. And the charge on the plates is also 0. And then we're back to electrostatic equilibrium. The mathematics of charging and discharging RC circuits follows what is called exponential growth and exponential decay. Which mathematical models of the ones shown would be expected to be seen in the current of the resistor? Well, interestingly, it depends on whether we're talking about charging the circuit or discharging it. So let's break it up into two parts. Charging and discharging. Go ahead and put your answers for each, and then I'll give my answers. When we charge an RC circuit with a battery, the current starts off high, and then it decays to a lower level. So for this reason, we want to use y equals AE to the negative KT for current in the resistor. What about when we're discharging it? Well, we showed over here, when we're discharging an RC circuit, the current would start high and then go down to a low level. So once again, we'll have y equals AE to the negative K times T. What about the voltage across the resistor when we're charging the circuit up? The voltage will follow the current. So it'll have the same type of formula. And when discharging, it'll be the same as well. What about the charge on the capacitor as we're charging the circuit up? In the example shown here, as we charge the capacitor up, we see that the charge approaches a limit. So that's what we want here. We want this type of formula. When we're discharging, though, we want the exponential decay formula. This is shown here in our example of discharge, where the charge on the capacitor starts off high at Q max, and then it goes down to 0 as time goes on. When it comes to the voltage across the capacitor, when we're charging, we want to build that voltage up to a maximum limit. But when we're discharging, we want it to decay. Now all we have to do to make our equations for RC circuits is to use the variables involved in RC circuits. By that I mean I'll rewrite the formulas now using the physics variables of I, V, and Q. For current in the resistor, our formula will be I equals I max or I naught, which is the initial amount of current, times e to the negative kt. For discharging, we'll have the same formula. You might also see it as I equals I max times e to the negative kt. For the voltage across the resistor, we'll want VR equals V max, or VO, e to the negative kt. The resistor's voltage will decrease towards 0 as time goes on. And for discharging, the same thing will happen. When we're charging up an RC circuit, the charge on the capacitor will be given by Q equals Q max times 1 minus e to the negative kt. But when we discharge, we'll have this. For voltage across the capacitor, that's something that's going to build up over time. It'll build up to a maximum voltage, which is V max. But when we're discharging, we'll start off at that initial V max, and it'll lose the charge over time.